This is a review of a homework problem on linear interpolation and also on cubic spline. So come to the course website at CHE 263 and then go to the homework. And we're going to be working on assignment 15. If you want to, just grab the files there. That's going to download a zipped folder, homework15.zip. And then if you come to downloads, for example, I'm just going to transfer that over to my desktop and then right click and extract it, and then we're going to work through some of these assignments. Okay, so these problems here. We have an intro and then also the homework. The intro is kind of like a template. It shows you some example problems that are similar to the ones that we're going to be working. And so let's go and open up both of those and then see some of the example problems, and then we'll work through the homework. Okay, so I'm going to go to desktop and then go to my homework 15 folder, and let me go ahead and open up my intro. First of all, that's going to show how to do okay, so we're going to be doing interpolation and curve fitting. I'm just going to skip this integration one right here. Okay, and go straight on down to interpolation. Okay, so I want to use the from SciPy interpolate. I'm going to use the interp 1D function, and I can use so this just shows me some of the data that I have right here, and the green line is the exact function, and so I want to come up with an approximation to that exact function by using the given data, or the blue points that you see there. Okay, so let's go down and we can come up with a linear interpolation using this function, use the x given and the y given, and then when I call that f linear function, create a new function f linear, and I get returned values YIL. Okay, so that's the linear interpolation. Okay, I can also use the spline function, and all I have to do there to change that is just do the kind equals cubic, and then create this new function, and it will do a cubic spline instead. Okay, so just looking at these different the data, the exact, which is the blue dashed line, and you can see the green line, which is the linear. So it's just going to take a linear approximation between successive points, and then the spline is going to do a cubic spline, take multiple points and set the derivatives at the edges of those splines equal to each other, so you have something that looks smooth and continuous. So that's going to be the red dashed line, which is going to be the spline. It's maybe just a little bit better approximation in this case. Okay, so let's go ahead and do this one for the homework problem. We'll use this intro as kind of a practice, and then copy in parts that we need for our homework. Okay, so we're going to go on to problem 2. So we have some data x given and y given below, and we want to find a linear interpolation YIL that corresponds and find the corresponding xi at a value of xi equals 0.54. And then we'll also do a cubic spline as well, and then we'll compute the error between the two and just see how well it works. Okay, so let's first of all just see what this function looks like. So I'm going to do x equals numpy linspace, and I'll go from 0 to 1. Okay, that's kind of where my data came from, and then I'll say that y equals, and then we'll do exp numpy exp of 4 times x. Okay, so those are just some points, and then let me go ahead and also plot this as well. Mat, so I've got to do the matplotlib inline if you're in IPython. If you're not, you can leave that out. And then I'll do import matplotlib.pyplot as plt. Okay, and then let's just generate a plot here based on this x and y data. I'll plot x, I'll plot y. Okay, and then we'll also plot x given and y given, and I'll do those as red points. Okay, and then let's go ahead and just look at those. Okay, so there I have my original function in blue and my points in red, and I want to have a linear and then also a cubic spline interpolation here. Okay, so let's go back to our intro file and just see some of the syntax there for doing this approximation. We have the linear approximation, and then we also have the spline approximation as well. So I just need to use that interp1d. So the first thing I'll need to do is just import this scipy.interpolate, okay, and that'll give me the interp1d function. Okay, so right up here I'll just paste that in. Okay, and then let's use the interp1d. We'll create a couple new functions. So let's do f1 is interp1d, and then we'll use the x given and the y given as well. Okay, and then I can evaluate that. Let me just do y1 equals f1 of x. So I'm going to evaluate all of these values between 0 and 1, and then let's go ahead and just plot that as well. Okay, so I have, let's plot that as a red dashed line. Okay, so there's my linear interpolation. I just had to give it the x points and the y points, and then it created a new function f1, and then I was able to call that new function at different values of x. In this particular case, I just want to call, so I just want to say that, let's see, we want to also compute y1 at 0.54. Okay, so y1, I'll just redefine that as f1 of xi. Okay, and then I can just print y1. Okay, so that equals 11.8, but my exact function is going to be just a little bit different. Okay, so I have my exact. Okay, so there you can see that my exact function is 8.67, and my approximation, my linear approximation, is 11.8. Okay, let's do a cubic spline and just see if we can get any better here. Okay, so I'm going to just copy this one. The only thing that I have to change is just change the kind. And if I come down here, you can see kind equals cubic. Okay, cubic, and let me make f2 and y2. And let's do those as a, how about just a black dashed line there. Okay, so we'll plot those. You can see the cubic is, it's a much better approximation than the linear fit there. But let's go ahead and see how good it is at 0.54. So let's go ahead and do a y2. I'll just redefine that at xi. Okay, so we have the two approximations there, and then the exact solution. So you can see the cubic is much closer. And then if you wanted to compute maybe the absolute error here, we're going to do the exact, and maybe we want to scale it by the exact value, so see a percentage difference from the exact. Okay, exact. Okay, so that is going to be 36% away there on y1, and then let's see what it is on y2. Okay, so only about 5.7% error there on y2. Okay, so that concludes problem number 2, where we had these, we were trying to do a linear interpolation between points or a cubic spline, either one. We just plotted this. We set up our two functions, f1 and f2. We either evaluated those at all these different x values here that were in the lin space, or we just evaluated them just at the xi values at 0.54, and then just showed graphically what was going on with this problem. Okay, so let's go on to problem number 3 now. So we have thermodata with heat capacities for the species. We had two temperature ranges for each species, and for the given array of temperatures K below, the corresponding C sub P over Rg arrays given for CH4 for methane. This is computed using the equations and the coefficients for the two temperature ranges given in the previous assignments. Okay, so if we were in the lower temperature range, we had to use these coefficients. If we were in the upper temperature range, we had to use these. We just want to develop one correlation that's going to work well over all temperature ranges. Okay, so here's some just some fancy programming here that helps us say, is it in one temperature range or another. We could also just create a new, define a new function to evaluate these. But let's just go with this code right here, and then just add to it to create this one function. We're going to use the polyfit to do this. So we're going to create a fourth order polynomial that covers the whole range of temperature data. Okay, and then we want to at each point compare the polynomial fit to the one given, and then report the maximum relative error that occurs over the list of temperatures, and then we'll plot the two versions to visually compare the original data and the polynomial fit. Okay, so we could do a linear interpolation or a cubic spline, but let's just come up with one polynomial that's going to fit all of the data here. Okay, so I'll have my polynomial here. Okay, let me come up with my polynomial. Okay, and then you see, let me just mention right here, I'm also have this temperature between 300 and 3000, and I have 100 different points. So those are going to be the 100 different points that I'm going to be comparing my model and my exact values. Okay, so let me come up with P4 is going to be Numpy. I already imported that Numpy earlier, and then I'm going to use polyfit, and I'm going to fit it these temperatures and then these C sub P Rg values. Okay, so all of those between for the A low and the A high, and I want a fourth order polynomial. So if you want a fifth order or sixth order, you could change that. I'm just going to have a fourth order. Okay, so let me go ahead and just compute that. And then if I print P4, okay, there are my coefficients of my polynomial. So it's the first coefficient times the temperature to the fourth, and then on down. Okay, so you actually have 5 coefficients there because it's to the fourth, third, second, first, and then to the no power. Okay, but let's go ahead and evaluate this, come up with a new function. So I'll just say function 1 is going to be NP. Now we'll use these polynomial fits, but look at the values that we want to calculate them at, and that's going to be our polynomials right there, these 5 numbers that we passed in, and then we're going to evaluate it at all of these different temperatures, and that's going to return F1. Okay, or I could do something like CP Rg new. In that case, just to have a new CPRG function. Okay, and then let's go ahead and just plot this. We'll do PLT plot and compare the temperature and the CPRG. We'll do that as a blue line, and then we'll compare that with the new version, which is CPRG new, and we'll do that as a red dashed line. Okay, so you could see from 300 all the way to 3,000. It's pretty good. There's a couple areas there down close to 300 that it doesn't do a very good job, but for the most part it does a very good job of using one expression to approximate the heat capacity over the whole range. Now let's say we had, let me go back down to this area right here, and let's go and just compute the errors like it asked us to. So we're going to have a relative error, and that is going to be numpy, and we'll use the absolute function. Okay, so that's going to be CPRG minus the CPRG new, and then we'll divide it by the real values. Okay, so we want to normalize this. We'll divide it by the real values there and come up with relative errors. Okay, let's see, what did I do there? Oh, I had an underscore here. Okay, so it said CPRG is not defined. It told me the line where that was present. Okay, and then let me just do the max on that. Okay, the maximum error then is going to be the max. Relative error is going to be NP max, and then I'll just plug in my relative error right there. Okay, and then I can print max relative error, and then you see the value. Okay, so 0.049. All right, so about 5% off, and that's probably right down here, right at the beginning where the value is, just deviates a little bit. Okay, so that concludes this problem. Let's go on to the last problem now. Okay, so now we have the following kinetic. This is R of t, the rates as a function of time were collected. We want to fit this to the following model function. Okay, so we have three unknown parameters, k, m, and then e over r, and those are adjustable parameters that we want to find so that our model best fits the data. We have these temperatures that we collected the data at, and then these are the r values. Let's go and just plot those just to take a look at them. plt.plot, and then temperature versus r, and we'll do those maybe as circles. Okay, let's see. Oh, I didn't run this top one first. Okay, it said it wasn't defined. Okay, so there is my there's my data. I want to try to fit this this model right here to that. Okay, so let's go ahead and just use curve fit. So this one, if you go back to the intro, we can come down to curve fitting, and we had the polynomial fit here, just with a couple examples on using the polyfit. General curve fit. Here's how we can define a custom function, for example. And then we're going to use the curve fit with that function, and then the x given and the y given. Okay, those are measured values for x and y. And then it'll compute our parameters. We can print those out. Okay, so here's an example of doing a curve fit. We're going to do that same thing for this homework 15. Okay, so let's see. What we want to do first of all is just go and define our function. And I'll just call that f of x. Okay, or you could say that's r of t, for example. But just avoid confusion with the numbers that are listed up there. I'll just do f of x, and then x will become my temperature. Okay, there are a couple other parameters that we need to insert here, like our k, m, and then I'll just lump in the EA and the RG into one parameter and call that EA RG. And then we'll return the k times t to the m times, and we'll use numpy exp. Okay, I put a couple spaces here just to make it a little bit easier to see. and then we'll do minus EARG divided by T. Okay, so there is our function that we've defined. If we want to evaluate that at different, different combinations of, let's see, I need to do this as, instead of T, okay, I'll just do that as X. Here's my function. Okay, so let's evaluate that at different temperatures. Maybe 300 different K values, 1.2. M values, I'll do 2. And then E over RG, and I'll do minus, I'll do 3000. Okay, oh, unbalanced parentheses. Okay, so that gave me a rate of 4.9. Okay, but I want to try to fit this function. I just came up with K, M, and E, A over RG values that I just came up with, but let's say I want to have that try to fit this function right here. I can use the curve fit. Okay, so let's come up with, I'll have my parameters. Okay, and then there's some extra stuff that is spit out from this function, so I'll just curve fit, and I'll do my function, and then I have my X given, which is my temperatures, and then my Y given, which are my R values. Okay, and curve fit is not defined. Okay, so let me go back in and import this because I need to do from SciPy optimize, and then we'll import curve fit. Okay, so make sure you do that first. I'll get my parameters, and then I can print my parameters out. Okay, so there are my 3 parameters for my K, M, and E over RG. Okay, and then I can, let's say, if I wanted to, I could define those, parameters 0, M, and EARG. Okay, so parameters 0, 1, and 2. Okay, so I have those now, and then let me go ahead and just see how well this fits. Okay, so I have all of these temperatures that I had up here, but let's say I just want a few more. I want more than just those temperatures. I'll do temperatures more, and I'll go between 500 and 1,000 instead of just 8. I'll do 100 of them. Okay, and then let me have the R fit value is then going to be that's going to be the F, this function, and with the more temperatures that I had, and then K, M, and EARG. Okay, so that's going to calculate at 100 different points the rates for me, and then let me just include this on the plot. Okay, so I had more temperatures, and then R fit, and we'll just make this a black line. Okay, and I think I lost that other plot. Okay, so let me get that one back. Oh, yeah, I split it up into 2. Let me just put that back, T and R, and then I'll do red dots. Okay, so there it shows the fit, and then also the red dots are going to be the sample values that I used to fit that arbitrary curve to the data.